Hello! Hopefully I can teach you something about the periodic table today. So first of all, we had this guy named Hennig Brand. He was a scientist in Germany who was constantly looking for the philosopher's stone, something that could turn metal to gold. Somehow he landed on the idea that maybe he could use a substance from urine. So in what must have been a very stinky process, he was able to isolate a white waxy substance from pee, which by the way he collected from his neighbors. Sadly, it did not turn anything into gold. However, it did glow in the dark. Brand called the substance phosphorus, or bringer of light in Greek, thus making him the first to identify an element. However, he kept all his research secret except from a few people, so this knowledge didn't become public until later. When Charles Boyle was like, oh yeah, here's the recipe for phosphorus that Brand tried to keep secret, now published to the world. Then along came Antoine Lavoisier, and he made the first modern chemistry textbook, and in it he included a list of 33 elements. He based them off of the 4 chemical properties listed below. And here is the table he created. As you can see, he had many of the elements that we see now on our modern table, such as oxygen or hydrogen. However, he also included light, which is lumiere, and caloric. Then, the infamous John Dalton came along and he proposed his atomic theory, which stated, all matter is composed of small, indivisible particles termed atoms, and atoms of a given element possess unique characteristics and weight. He also came up with these little symbols for each element, which was used for a time before this guy, John Jacob Berzelius, came along and was like, yo, Dalton, why are we using all these symbols? Have you seen this handy thing over here called the alphabet? So he went on to create letter symbols for each element based on their Latin name. Many of the symbols he came up with we still use today. He also did extensive research on almost all the molecular weights of the elements known at the time, as well as discovering many new elements in his own lab. Then, throughout the years of 1829 to 1865, several notable attempts were made to arrange the periodic table, by grouping them in groups of 3, by finding relationships within specific groups of elements, and then the telluric screw was especially interesting. It was something you twisted to try and find relationships. Be glad that we don't have to carry those around in our backpacks. And then Newlands came up with the rule of octaves, which was the idea that elements that were 7 electrons away from each other had similar properties. His work wasn't published when he first introduced the idea, though, because people thought that his octaves were useless. And then along came the man, the myth, the legend, Mendeleev! Woo! So Dmitry Ivanovich Mendeleev came up with the basis of our modern-day periodic table. He had it published in The Principles of Chemistry. Mendeleev took his concept even further by stating that it was possible to predict the properties of undiscovered elements. He then proceeded to make predictions for 3 new elements, aka aluminum, boron, and silicon, and suggested several properties of each, including density, radii, and combining ratios with oxygen, among other things. The science world was perplexed, and many scoffed at Mendeleev's predictions. To take matters further, he also stated that a few widely accepted atomic weights of a few elements were wrong. So, for a while, his new table was disregarded. People just kind of moved on and didn't care, until this Frenchman discovers what he calls gallium, but is now known as aluminum, and then a few others are discovered, and all of a sudden, Mendeleev is everyone's new favorite friend. Mendeleev becomes one of the few great scientists to be celebrated and appreciated for their efforts while he's alive. However, arranged on his original periodic table based on atomic weights, there was a problem. Tellurium and iodine were right next to each other, but they didn't seem to fit in their column that they were placed in due to atomic weight. Their chemical properties would match better if they were switched. Mendeleev assumed that their measurements were simply wrong. However, every time he measured, he found the same data as the original. Cobalt and nickel also showed the same problem, although it was discovered later that they were just not accurately measured. So, when argon was discovered, the masses of argon and potassium were reversed. Henry Moseley found the reason for these apparent exceptions to the rule. As a result of Moseley's work, the periodic law was revised. He stated that physical and chemical properties are a periodic function of their atomic number, rather than mass. This better explains the gaps in the table. The atomic number of an element indicates the number of protons in the nucleus of each atom of the element. The atomic number also indicates the number of electrons surrounding the nucleus. Herewith, he created the modern periodic table in which each succeeding element has one more proton and electron than the former element. So what's the impact and importance of having them in a table like this? I'm going to briefly go through a few effects observable based on how the periodic table is set up. So based on a neutral atom's radius, you can see that you increase going down because every time you go down, the atom has one more electron energy shell. It also increases as you move from right to left because each of the atoms on the same row have the same amount of energy levels, but you slowly decrease in the amount of protons you have as you move to the left, which means there's less of a positive charge holding the electrons tightly, allowing the atom to be a little bit more spread out, which leads us into the shielding effect, which is the ability of an atom's inner electrons to shield its positively charged nucleus from its valence electrons. So when you move down, you get an increased amount of levels in between the valence electrons and the positive nucleus, which means the valence electrons are more shielded. Shielding effect affects both atomic radius, as we talked about, and how easily a valence electron can be pulled off. And then we have electronegativity. That's the ability of an atom to attract an electron. As you can see, fluorine has the highest electronegativity. This is because it has 7 electrons in its valence shell and really wants to fill the octet rule of having 8 electrons in its valence shell. So it, as well as the other halides, are pretty electronegative. On the flip side, the alkali earth metals and alkali metals have really low electronegativities because they only have 1 or 2 valence electrons. So they would rather lose their electron to fulfill the octet rule than try and gain 6 or 7 electrons. Electronegativities help us determine what type of bond can form for different elements. So I hope that was helpful to see that the periodic table wasn't just thrown together haphazardly, but it actually took a lot of time and a lot of smart people to come together. Thank heavens we have it today to help in all of our scientific endeavors.